And voila. So I'm going to start now. Today's the second class about thermal conversion. We're going to talk about biomass and biogas thermal power plants. Just a quick reminder about last week's class. You know, when we're converting thermal energy to mechanical energy, or as I said, to disorganized form of energy to an organized form of energy, which can be work, mechanical work, or it can be electricity or kinetic energy, and so on. Okay, so this conversion of a thermal source to work or electricity always can be put in this way. You have a heat supply, a heat reservoir, as we say, which works at a temperature TQ. Okay, so this flux of heat between the heat reservoir and the cold reservoir, whose temperature is TF, from this flow of heat, you can insert a thermal machine, which will somehow extract some amount of work, of mechanical work. Okay, and I said to you last week that for the industrial or large-scale applications, the heat absorber is always the environment. It can be the atmosphere. So when you look at the thermal power plant and you see a cooling tower, for instance, you know that heat's being rejected to the atmosphere. Or it can be a lake or a river or a sea and so on. So the reason why I'm emphasizing this is that we cannot control the temperature of the heat sink or the heat absorber because it's always related to the environment. On the other side, we can control the temperature of the heat supplier because it can be, as it's written here, it can be a combustion reaction, which we are focusing today. It can be a nuclear reaction, or even it can be the sun through solar concentrators, for instance. So in some way we have control of the conditions, of the operating conditions here, and that's one of the main variables in order to optimize how this thermal machine works. Okay. Another thing that I've mentioned last week is that there are different types of energy that we can classify in microscopic and microscopic. Okay, so microscopic forms of energy are related to the center of mass of the system, and in that case, for instance, the kinetic energy is more related to wind energy, and the potential energy, the microscopic potential energy, is more related to hydroelectric power. The microscopic forms, such as molecular translation, which is directly related to temperature, is, well, related to geothermal or solar thermal energies. When you talk about chemical energy, that's the focus today, actually. You have to use, or you have to engineer a chemical reaction in order to free the energy associated with these liaisons here, so it's more related to thermoelectric power plants. And you may also have a nuclear power plant, in which case you have to have a nuclear reaction taking place inside the reactor. Okay, so I'm going to review all this stuff because we're not going to look in more details than today. These several types of thermal energy generation. Okay, a geothermal plant, as it's shown here, takes the heat from the underground. Okay, so it works more or less like this. You pump cold water through a rock that receives heat from the center of the earth, actually. Okay, so this water flows to this other pipe here, and in that way it absorbs heat. Okay, earth is heat. So here you have high pressure, high temperature steam, then expansion on a turbine, and heat rejection to the atmosphere, and that completes the cycle. Okay, this turbine drives a generator which inserts electricity on the grid. Okay, when you change from a geothermal source to a solar thermal, the only thing that changes is the source of heat. You know, I'm going back one slide. You see here the source is Earth, is underground, and here is the sun. So you have heat absorbers here that absorbs heat from the sun, and the same way you have high pressure, high temperature steam here, expansion, work generation, conversion to electricity, and rejection to the atmosphere. Okay, when you change from solar to a thermal power plant, which we're going to see today, it actually is based on fuel combustion. So somewhere you have combustion of a fuel. We're going to look today for biomass as fuel and also biogas. So the same way, you have cold water, hot steam, high pressure, expansion, generation of work, and so on. Okay, so I'm not going in much detail here because we're going to come back to this type of power plant. You can have a thermonuclear power plant based on fission reaction. So what changes is that instead of having the sun or Earth is underground as a heat source, you have a fission reaction taking place inside the reactor. We're going to look in a little bit more detail this kind of plant. So this is the reactor building. I'm going back one slide. So you have the reactor building here. Inside you have the nuclear reactor. And actually, the thermonuclear power plant usually is built in two cycles. A primary cycle, which takes direct contact with the nuclear reaction, and a secondary cycle, which corresponds to the thermodynamic cycle, to a Rankine cycle, for instance. So you see, there's the reactor. You have the primary cycle, the water from the primary cycle circulating here. You just have hot water, pressurized hot water, typically 200 or 300 bar at 300 degrees, for instance. So it's liquid water, but very hot. Okay, so this water goes inside a boiler, and it supplies heat to water from the secondary cycle. So this water, this is cold water, high pressure cold water. It's being transformed into steam here. So it will drive a thermodynamic cycle. Okay, just to remind you, if you're not aware, what is a fission reaction? Actually, is a breakdown of the nucleus of the atom, like it's shown here from uranium. When a neutron hits the center, the nucleus of a uranium atom, it splits in two. Okay, and if you make a mass balance here, okay, if you add all masses from these two products, and also for adding the masses of these neutrons that are emitted, you see that the mass on the right-hand side of the equation is a little bit smaller than the mass on the left side of the equation. So the difference in mass is related to the amount of energy that is released. And this we have seen, I think, in our first class. This amount of energy, let's say this power, this rate of energy release, is related to the rate of mass destruction multiplied by the velocity of the light to the square. Okay, so you see that the amounts of energy involved are very, very big. So that's a very important energy source. Just to look in more detail, the nuclear reactor. Here's the reactor. Okay, the nuclear reaction is taking place here. Here you have fuel rods. So if you want to increase the rate of fission reaction, you just push down these rods and you it's like in accelerating your car, okay? So the nuclear reaction takes place here, and the primary cycle, or the primary circuit, okay, takes place here. So here you have cold water, pressurized cold water, which absorbs heat from the reaction, and this water goes to the boiler and releases this heat to the working fluid of the secondary circuit. Okay, and so here you have high pressure, high steam, with high pressure, high temperature steam, which drives a thermodynamic turbine, for instance, okay, for energy, for electricity generation purposes, for instance. Okay, just to take a look inside of the boiler, you have heavy water here coming inside here. You have a tube bundle here. So this heavy water is circulating here and immersed. This tube bundle is immersed in water from the secondary circuit. This water is heated by this tube bundle and it transforms into steam. Okay, so that's in very general lines how the boiler of a nuclear reaction, nuclear power plant works. Okay, just a bit of information about a thermal power plant based on fuel burning. Actually, you see, I mentioned that there's always a combustion reaction here.
Professor?
Yeah, go on.
Professor?
Yeah?
I have a question. Is it only a nuclear fusion that you can generate energy from? Is it possible to generate energy also from nuclear fusion?
No, it's not technically possible. That's the subject of research for the last, I don't know, 50 years. Actually, I worked on nuclear fusion myself during my PhD, and it's still not ready for industrial applications. So in the 90s, for instance, when I worked on this subject, the problem was to start the reaction. You know, we can make a fusion bomb. The H bomb actually is a fusion bomb. We can start the reaction, but we cannot control the reaction in order to generate electricity in a controlled manner. Okay, so in the 90s, the problem was to start the reaction, and that was accomplished by laser beams. With lasers, you can squeeze two hydrogen atoms, for instance. Let me just make a quick drawing here. Okay, so if you have a H2 atom here and H2, and somehow you have to put these two atoms in contact in order for them to become a helium atom. Okay, so the initiation of the reaction was accomplished through laser technology. The problem now is not starting the reaction. The problem now is to confine the reaction and to control the reaction. You know, this reaction, H2 giving place to helium, that's exactly the same reaction that takes place in the sun, okay? And let me ask you a question. What confines and what squeezes H2 atoms in the sun? You know, it's the gravity, the gravitational field of the sun that makes that. And we don't have this kind of force here on Earth. So what we try to do is to use magnetic fields in order to confine this reaction and to be able to control the reaction. You have to be able to accelerate and decrease the reaction rate in order to control the amount of heat that is being generated. Okay? So today, if you go to these labs in the world, you see they are all working on confining the nuclear reaction, the fusion reaction inside a magnetic field. Those are the tokamaks. Tokamaks, a type of reactor that is based on nuclear, magnetic fields. So that's the current status of the research today. But there are no power plants based on this type of reaction. Only nuclear fission, okay? And that's been done for the last 50 years. I don't know. Okay.
Okay.
Okay. So moving on, I'm going to talk a little bit about a thermal power plant, and we're going to revise all the thermodynamic equations in order to be able to better analyze this type of plant. And just emphasizing that today we're going to focus on biomass and biogas power plants. Okay, so there's always a combustion reaction, which actually is you take your fuel mixed with air, or it can be pure oxygen. Then you have combustion gases and thermal energy. Okay, thermal energy is going to be converted to electricity. So the combustion reaction can be something like this. I'm using methane here just for simplicity, and because in a few slides we're going to calculate some things about this reaction, chemical reaction. For instance, we're going to calculate the combustion temperature of this reaction. Okay, I'm going to show you how. So we can use methane just for simplicity. That's the stoichiometric formula of air, if you use air as your comburant, okay? So you need 2 moles of air to burn 1 mole of CH4, and you generate 1 mole of CO2, 2 moles of H2O, and nitrogen, which is present in atmospheric air, okay? Is not, if the temperature of the reaction is not high enough, it's not going to react. So you have cold N2 here, and you have hot N2 here. So the role played by nitrogen is very important in controlling the combustion temperature. Because if you don't have nitrogen and you use pure O2, we're going to calculate that in a moment. The temperature here can rise to 3,000 degrees, for instance. Okay, so that's good in terms of thermodynamics, but you don't have materials that are able to operate, commercial materials, I mean, that are able to operate in this kind of temperature. Okay, so we're going to see that in a few moments. Yeah, I'm going to talk first about gas thermal power plants, or actually the Brayton cycle. Just a reminder, today's class, we're going to make a bit of a tutorial, okay? I'm going to make some engineering calculations, thermodynamic calculations, just to show you how it is possible to use this kind of thermodynamic property software in order to make these calculations. Okay, so let's see the Brayton cycle, which is a cycle associated with gas thermal power plants. Okay, I think I've shown this picture before to you. This is well, this is the reaction. Going back 2 slides, let's see how this reaction is actually used in order to generate electricity. So you have air, okay, being entering the compressor, being compressed to the pressure of the combustion chamber, and here you mix your fuel, methane, just for simplicity. Okay, so the combustion reaction takes place in the combustion chamber, and you have a certain temperature, or I should say at a certain temperature, because this parameter here, the combustion temperature, actually is a design parameter. You have to optimize that. You know, from the thermodynamic science, you would want the highest possible combustion temperature, but you have to consider all the problems associated with the materials. So you have to find a trade-off between in a high enough temperature that goes well with all your materials, especially in the turbine. Okay, so here you have hot gases, high pressure. They are expanding on the turbine, generating mechanical work. Part of this work is used by the compressor, and part of this work, the surplus work, actually drives the generator. Okay, and then you exhaust gases to the atmosphere. Okay, if we want, I'm going to show you how to calculate this temperature and also how to control this temperature, because, as I said, you have material concerns here. Not only material concerns, but also pollution concerns, because if this temperature here is excessively high, nitrogen is going to start to react with oxygen, and you have nitrogen oxides being formed. And this is a very dangerous pollutant that you cannot afford to emit that to the atmosphere. Okay, so you want to control, you want to limit this temperature for two main reasons: materials and formation of nitrogen oxides. Okay, well, when the equation that you're going to use to calculate that is the first law of thermodynamics, based on a control volume around the combustion chamber. Okay, so that's the first law of thermodynamics. Okay, heat minus work equals the net output of energy associated with the mass flow. Okay, so that's it. When we do that in the with the volume control volume associated with the combustion chamber, let me make a quick drawing here. The control volume is around the combustion chamber. Okay, that's the control volume, which is associated to this equation. So you see, you can assume that this combustion chamber is adiabatic. Okay, you're not losing heat through the walls. This can be by construction. You add isolation. Okay, there's no work either. So you only have to account for these quantities here. Just a reminder, the inlet temperature at which you calculate all enthalpies is the temperature at the exit of the compressor. So it's typically 200, 300, 350 degrees Celsius here. Okay, and the outlet temperature is the combustion temperature, which is an unknown. This temperature here, we must solve this equation in order to calculate this temperature. Okay, I'm going to show you how to do that. Okay, so let's write down all the equations. Going back one slide. Heat is 0 because the chamber is adiabatic, no work. There's not a turbine there. There's not a moving surface inside. Okay, so you have 0 equals to the difference in the enthalpies. Okay, as I said, the inlet enthalpies are calculated at 400 degrees. This number 400 degrees is just for simplicity. I'm setting this number just to avoid having to calculate the temperature here. Okay, no problem. So we want, in this equation, we know the enthalpies of every species of oxygen, of nitrogen, okay? And also we know the relation of enthalpy of every output species, CO2, H2O, and nitrogen, with respect to the combustion temperature. So we have to express these enthalpies in terms of this temperature in order to solve this equation to calculate this the combustion temperature. Okay, so let's see how this can be done. This is the reaction, because we're going to use Hess's law in order to calculate that. The problem, it's not practical to calculate that directly, because the temperature on the right-hand side of the equation is not the same as the temperature on the left side. Okay? So what we're going to do, we are going to use, as I said, the Hess law, which just follow my reasoning. Suppose instead of reacting the fuel and air at 400 degrees, suppose that before reacting, we cool down the fuel and air to, let's say, 25 degrees. So we somehow remove heat from fuel and from air in order to cool it down to 25 degrees, okay? Then you allow the reaction to take place. So CH4 is reacting with O2. You have CO2 and H2O. You also have a release of heat, okay? And well, you also have nitrogen. Now, this nitrogen, 7.52, is actually 2 times 3.76, okay? So I'm assuming that N2 is not reacting, okay? And we do this inside a calorimeter. So we know a priori that this reaction releases heat. So in order to maintain the temperature at 25 degrees, you have to remove heat, okay? Then, when all species have reacted, we heat this mixture, the combustion gases, to the final temperature, which we are denoting at TCOM, combustion temperature, okay? So this corresponds to Hess law, and we're going to do all the calculations like this. Why this is so? Because we have data, standardized data of this combustion reaction at 25 degrees. Okay. For instance, we know the enthalpy, the reaction enthalpy at 25 degrees, but we do not know the reaction enthalpy at 400 degrees. Okay. So that's why we do. So all heat exchanges associated with this pathway. Okay. I don't know if you understand. Instead of taking this direct pathway, we are taking this pathway. We cool, we allow the reaction to take place, then we heat. Okay? And what Hess law states is that the energy balance is the same as we can take the direct path or this indirect path here. Okay? So the energy balance is the same. So in order to do that, we have three types of heat associated, okay? We have heat associated with cooling, which is specific heat because all species are just being cooled down. They do not change phase and they do not react chemically, I mean, okay? Then we have combustion enthalpy associated with the combustion reaction. And this is the type of data that we have from a calorimeter. Okay, so we're going to use that for our calculations. And we also have the heat necessary to heat the combustion gases from 25 to the combustion temperature. Okay, so we have to assess all these three numbers here. Okay, I'm going to show you how. So how can we assess the combustion enthalpy change? Actually, we do that in a calorimeter. We measure that. There are some formulas that allow you to, some models that allow you to calculate the combustion enthalpy. Okay, but you have this standardized, so you can look at your tables and you get the combustion heat of methane, for instance. Okay, so this is a parameter that is measured at the laboratory. Okay, so we do exactly as it is shown here. We have a means of maintaining the temperature at 25 degrees. So the reaction is going to take place inside this chamber here. You mix air or pure O2 with your sample, with your fuel, which can be methane or sugarcane bagasse, okay? And outside you have what we call isothermal bath, okay? Which is responsible for maintaining the temperature at 25 degrees. So you let the reaction, you allow the reaction to take place, and then you measure the amount of heat that you have to remove from the combustion chamber in order to maintain it at 25 degrees. Okay? This amount of heat is exactly the combustion enthalpy. Okay? So that's how we measure this parameter here. And it is very, very, very usual to do that at 25 degrees. If you have this type of equipment at your laboratory, which is very common actually, you can do these measurements at 30, at 50, you can change this temperature for some reason. I don't know, in order to have a more accurate assessment of these energies associated with the reaction. Okay, so that's our first parameter. And when you go to the necessary charts, we get this number here for methane. Okay, so every kilogram of methane reacting with air releases 50 megajoules. Okay, the minus sign here means that the reaction is releasing heat, not absorbing heat. Okay, that's our convention. Remember Newcomen's thermal machine. You supply coal to Newcomen's machine, and Newcomen's machine drains water from the bottom of the mine, so it produces work for you. You supply coal, the machine produces work, so supplying heat is positive, and supply or generating work is positive. Okay, so this is the data for methane. I'm just converting here to instead of using the combustion enthalpy in kilograms or per kilogram, it's more easy to use it as per mole. Okay, so I'm just multiplying by the molecular mass in order to convert this number from megajoules per kilogram to megajoules per mole, okay, of reaction. Just a simple calculation. Another parameter that we need is the specific heat at constant pressure. I'm going back to a few slides here. Since we have to cool from 400 to 25, and then to heat from 25 to the combustion temperature, we're going to need the corresponding specific heats. Okay, so we need the specific heat of methane, because we're going to cool methane from 400 to 25. We need the specific heat of oxygen, and so on and so forth. Okay, so the data is here. That's the specific heat at constant pressure of methane, 35.69 joules per mole Kelvin. Okay, the same data for oxygen, for nitrogen, CO2, and H2O. A reminder, the specific heat of H2O changes a lot, so I'm just using an average value for these calculations. Okay, I'm going to show you how you can obtain this data. I can do it now, right now. Okay, so for instance, how did I get this number, 41.55? This is the tutorial part of the class. Okay, I use there are several types of thermodynamic property software. I like to use this one, RefProp. It has a student version, a free student version that you can download and install and use it. It's very useful. So I'm going to try to show you how I managed to get this number here. Okay, so the first thing that you do is, well, you choose your substance. We we can choose among many. I'm going to choose water, okay? And then I want to calculate everything in molar basis, okay? So I'm going to change, because the default is mass basis, I'm going to change to molar basis, okay? And I want to calculate the specific heat. So where is it? Cp. Okay, so Cp, I'm going to calculate specific heat, okay? And let me go back to my PowerPoint presentation. I need the specific heat of water between 25 to the combustion temperature, okay? Which is a little bit smaller than 1000 degrees, okay? So I can, for instance, calculate the specified state points, 25 degrees, and let's say that I have 0.1 bar, okay? 50 degrees, 0.1, okay? 100, 100, 0.1, 500, 0.1, okay? So you see, you have here the specific heat for different temperatures and pressures. You can also vary the pressure. So what I did was calculate an average number representing all these specific heats, okay? Is there any question about this calculation that I did? Okay. So that's why I'm using this average number here, because it changes a lot for water. Oh, yes, just an observation. Why I'm fixing a pressure as low as 0.1? Because, you know, suppose that this reaction is taking place at, let's say, 1 bar, okay? Everything is at 1 bar, atmospheric pressure, okay? You know, 1 bar is the sum of the partial pressures of all components, okay? Of all components. So I just figuring that 0.1 is the partial pressure of H2O, okay, in the vapor phase after the reaction, okay? So just for as a hypothesis, the pressure of H2O is 0.1 bar. You can verify. Let me just erase this. You can, for instance, verify the sensitivity of the specific heat in terms of pressure. For instance, you can say that it's 25. Oh, well, you can calculate the partial pressure. There is no problem. I just want to show you that it's not very sensitive. So if I put 25 degrees, 0.1 bar, the temperature is going to be the same. I'm going to double the partial pressure, 0.2. You see that the specific heat, it's almost insensitive to the pressure, okay? Okay? So, okay, go back. Yeah, let me just get my pointer back. Sorry, here. So this is the data that I'm going to use to calculate, to make all this, to make this energy balance here, okay? Okay, let's go. So the equation is the heat necessary to cool down the fuel and air plus the combustion heat plus the heat necessary to heat the combustion gases from 25 to 400. Okay, so we're going to calculate all this. So first, this number here, okay, the temperature variation is 25 minus 400. And here I add all CPs multiplied by the number of moles involved in the equation. Okay, so this number 1 here is actually 1 mole here. Okay, the number 2 moles of air, actually is this number here, 2 moles of air. Okay, this is Cp of oxygen plus the Cp of nitrogen multiplied by the number of moles of nitrogen per mole of oxygen in air. Okay. Then we have the combustion enthalpy, and then the heat necessary to heat from 25 to the combustion temperature. And the combustion temperature is unknown right now. Okay. So I do the same. This is a Cp of CO2. I have 1 mole of CO2, 2 moles of water, and 7.52 moles of nitrogen. Okay, everything's been multiplied by the delta temperature, which is the combustion temperature minus 25. When we insert all the data that we have from the previous slide, we obtain for the combustion temperature 2,737 degrees. Okay, you see that it is excessively high. So, for instance, it's very hard to find commercial and more or less cheap materials that work around this temperature. Okay, that is applicable at this temperature. But you also have another concern that at this temperature, this is very important what I'm going to say. At this temperature, it is not true that nitrogen is not going to react with oxygen. Okay? So at that temperature, you should change this reaction. You should add some amount of NO1 and NO2 and make the necessary calculations. Okay? So we're not going to do that because this is not a workable temperature. We have to do something in order to control, to limit this temperature below, let's say, 1,000 degrees. Okay? So the way that we do that, I already mentioned that nitrogen is stealing some amount of heat because its nitrogen is entering at 25 degrees and it's coming out of the reaction at the combustion temperature. So there is heat associated. There's heat being stored by nitrogen. So what we do, we're going to supply more than necessary air in order to cool the reaction. Okay? So we work, as we say, with excess air, and we can do the calculations. Okay? So this is the stoichiometric reaction, as I showed. Okay? 2 moles of air per mole of CH4. And if we want to use some amount of excess air, we're going to create a parameter. E is for excess air. Okay, and we're going to insert this parameter here. Okay, so 2 moles is being multiplied by 1 plus E. E is in mole per mole. Okay, and when E is 0, we have stoichiometric reaction, as we did right now. Okay, so when we do all calculations, okay, the only difference is that in addition to CO2, H2O, and nitrogen, we also have 2 times E times 1 mole of air that is not reacting because the stoichiometric amounts of air already reacted with methane. Okay, so I leave it to you to make all the calculations here as a suggestion for your homework. Okay, and when you do this calculation, we can actually calculate the combustion temperature in function of the excess air. As I mentioned, when E equals 0, okay, we have stoichiometric combustion, and we have the previous result, which was 2,700 degrees. Okay, and when E increases, the temperatures drop, and you can determine the amount of excess air that you have to have in order to control the combustion temperature for material concerns and also for pollution concerns. Okay?
Teacher.
Yeah, go on.
About the nitrogen, is a constant, this number 3.76?
Yeah,
it's a constant.
Yeah, it is, because that's the constitution of atmospheric air. Okay? Atmospheric air is 70% of nitrogen, 21% of oxygen, and so on. Okay?
Is there another one, 70.52 is you injecting the reaction?
Yeah, we actually 7.52. I just simplified here. When you, I'm going to show you where. Yeah, here. 2 times 376. Okay.
Oh yeah.
Okay, it's equal. Yeah.
Yeah, sorry.
Yeah. I should have written like this. It's simpler. Okay.
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 Thank you.
Sorry for that. Okay. So, well, I wanted to show you this because this is a simple way of calculating the combustion temperature. It's interesting because I can exploit this problem related to the control of the combustion temperature. Okay, but as far as we need only to make a thermodynamic analysis, there's a simpler way of doing that. Okay, using charted data. Okay, so I'm going to show you a simplified analysis of this problem, and we're going to make the calculations assuming something different. Okay, I'm going back a few slides. Where's my, yeah, here. So this is the actual gas power plant. We react air with fuel, with natural gas, methane, okay? And here we have combustion gases composed of CO2, H2O, and nitrogen, okay? We could do differently. We could do this, okay? Instead of reacting directly in the combustion chamber, we could do this. We could react air and fuel and methane. Okay. This reaction I showed you, it releases heat. Okay. You can think that this combustion chamber here is our calorimeter. Okay. So it releases. This is the reaction heat. Everything is at 25 degrees. Okay. And this heat released by the combustion reaction is going to be supplied to an pure air thermodynamic cycle. Okay, so you could do this. Is possible. This is not impossible. Okay, so you could take air, you compress, then you heat air with the heat supplied by the combustion here. Then at this point here, you have air, always air. It's not, there's no chemical reaction taking place, so you have air here, okay, at high pressure, because the compressor compressed the air, increased the pressure, and also high temperature, okay, because the working fluid, which is air, absorbed this amount of energy here, okay. So you have high pressure, high temperature, then you expand air in the turbine, you produce work, and so on. Okay, so you can do this calculation, and you can assume that the heat supplied to this pure air cycle is exactly equal to the combustion heat measured in a calorimeter. Okay, for which we have charted data, as I showed you. Okay, we can do the calculations. I'm going to show you how. Okay, so first let us introduce some kind of nomenclature. Okay, so point 1 is air at ambient temperature and pressure. Okay, 2 is air at the exit of the compressor. 3 is air at the exit of the heater. Okay, and 4 is air at the exit of at the outlet of the turbine. Okay. Okay. So what we call a Brayton cycle is composed of is defined as a series of thermodynamic transformations. Okay. Between 1 and 2, we're going to assume that it is a isentropic compression. Okay. Isentropic meaning that there's no heat exchange, so it's adiabatic, and there's also no friction, internal friction, and no other types of irreversibilities, okay? Between 2 and 3, it's isobaric heat absorption, okay? Between 3 and 4, isentropic expansion. And between, let's say, 4 and 1, it's 5 and 5, it's wrong here, sorry. So between 4 and 1, air is rejecting heat to the rest of the atmosphere at constant pressure. Okay, so that's the definition of what we call Brayton cycle. We're going to do the calculations here, okay? So this is the cycle shown. This is the actual cycle in a temperature entropy diagram for air, okay, which I generated with a ref prop. I can show you right now how to do this, okay? First thing, you have to change substance. Air is a pseudo-fluid, which I already have it here, okay? Dry air, nitrogen, oxygen, and argon, okay? Yeah, let me just go back to mass base units here, mass base, okay? Yeah, and we can plot a TS, generate the TS diagram. No, plot TS diagram, okay, at different pressures, okay? So, yeah. So actually we are working, this is, the temperature is too low, okay? It's at minus 100 degrees. I'm gonna do it again, plot TS. Let's say, let me see, between 0 and 1000 degrees, okay? So between 0 and 1000 degrees, okay. And that's the diagram, TS diagram. Can zoom this region here. That's the TS diagram for air, okay? Okay, so remember the definition: isentropic compression, isobaric absorption of heat, isentropic expansion, and isobaric rejection of heat, okay? So between 1 is atmospheric pressure, 1 bar, 25 degrees, so that's the GPS coordinates of this thermodynamic state, okay? Isentropic compression means that the path is vertical, so we go from 1 bar to the working pressure, which I fixed at 26 bar here. This is the design parameter, okay? So by increasing pressure through a vertical path, we attain 26 bar, which is the arbitrated working pressure. So the temperature is 425, okay? Then we absorb heat from the combustion chamber at constant pressure. So pressure is going to remain constant at 26 bar until we reach the maximum temperature. Let's say that it's 1000 degrees. Let's just assume that is 1000 degrees, okay? Then we expand isentropically to the atmospheric pressure, okay? So we go down through a vertical path until we reach the atmospheric pressure, okay? And we can calculate the temperature here, okay? I'm gonna do this with ref prop as I showed you, okay? So let's do it together, or try to follow me. I'm going to calculate on specified points. Okay, so the first point is 1 bar, 25 degrees. Okay, so 1 bar, 25 degrees. Enter, and you have all thermodynamic data. We need especially enthalpy for the energy balances. Okay. Next, our working pressure, let me see, I'm arbitrating at 20 bar. We're going to set our mass flow, just to enable our numeric calculations, okay? 10 kilograms per second. We are processing 10 kilograms of air per second. And the working pressure is 20 bar. Okay? So next, the working pressure is 20 bar. And since the process between 1 and 2 is isentropic, this means that the entropy is the same. Okay? So I know the pressure is 20 bar, and the other, as I say, GPS coordinate is the entropy, which is the same because the process is isentropic. So 3.8843. Enter, and then you have all the remaining data. Okay? Then we're going to absorb heat until we air reaches the maximum temperature, which I'm somewhere I stated it is 1000 degrees. I'm not sure. Let me see. What did I do here? Air 20 bar. Yeah, I don't know why I have this temperature here, but well, anyway. So I'm fixing the pressure, okay? And if temperature is 1000 degrees, enter. You always need two coordinates, okay? In order to specify the state, in order to calculate all thermodynamic properties. And I'm not showing all right now, okay? You can go back here, for instance, and properties, and you can ask for the internal energy, you can ask for the viscosity, you can ask for many types of thermodynamic properties, okay? So we are at point 3, okay? Maximum temperature, maximum pressure. Then we're going to expand isentropically to the atmospheric pressure, okay? So the pressure here is going to be 1 bar, and the process is isentropic, so the entropy is not going to change. 4.5778. Enter, okay? And that's it. I have all the enthalpies that I need in order to make in order to apply energy conservation equations. You see, that's the temperature of the exhaust gas. It's still very high, 315, so it contains a lot of thermal energy, which is the reason why this enthalpy is relatively high, okay? Okay, so that's how we determine all enthalpies, okay? And once we determine all the enthalpies, we can calculate all associated energy. So the work, the compression work, I can determine, okay? So this equation comes from applying the first law of thermodynamics to the compressor, okay? So that's what I get. I get that the necessary work is the mass flow of air times the variation in enthalpy. Okay, when we do the calculation, I obtained 4.007 megawatts. Okay, negative here means that this process absorbs work. Okay, so that's why we obtain a negative sign. Okay, then yeah, I did something differently here. Okay, I arbitrated here that the rate of heat absorption from the combustion of methane at 10 megawatts, okay? How do I do this? Just burn the necessary amount of fuel, okay? So the enthalpy at state 3 can be calculated by the same equation, first law, but this time on the heat exchanger, okay? So I don't know if you understood, okay? The heat, going back a few slides, the heat absorbed here, okay? I'm going to say it is, I don't remember, 10 megawatts, okay? I'm going to assume that this heat is 10 megawatts, okay? how is it possible to obtain? I just burn the necessary amount of methane, okay? So if I assume that, this is just to show you how we can make the calculation, okay? So if I assume that this is 10 megawatts, I also know that this is the mass flow rate of air times enthalpy variation. So I know this, I know this, I know this, and I can determine this number here, okay? When I do the calculations, I obtain this result here, okay? So instead of doing what I did, because when I showed you how to calculate here, I was showing you, instead of setting the amount of heat absorbed, I just said the temperature was going to be 1000 degrees, okay? Let's do something different. Suppose that the pressure is 20 bar, okay? And the enthalpy is going to be this number, this result here, because we fixed the amount of heat absorbed, okay? So when I put 1825.27, so the enthalpy is going to be 1825.27, enter, and I have all the corresponding results, okay? So this is just a demonstration of how we use this kind of software, okay? Okay, so going on, by assuming that P3 equals the maximum working pressure, H3 is what we calculated, okay? We can determine all parameters at point 3, and we determine that the temperature is 1275 degrees, okay? And then we can, by considering that the pressure is going to be 1 bar, and the enthalpy, the entropy does not change, so we can input 1 bar here, 4.8154, and we get all the results. You see, 461 degrees is the exhaust temperature of the gases, okay? And you see that it contains a lot of thermal energy, okay? Okay, so that's the calculations. When we want to obtain the absolute values, okay, so multiplying everything by the mass flow rate of processed air, we need 4 megawatts in the compressor. We generate 9.48 at the turbine, and we exchange, we have to reject 4.53 to the atmosphere, okay? That's being sent to the atmosphere. So it's almost 50% of the work generated at the turbine, okay? So our efficiency actually is the net amount of work, 9.48 minus 4.01 divided by 10 megawatts. This is the amount of heat absorbed from fuel. When we do the calculations, we obtain 54.7%, okay? And we can compare that with the efficiency of a virtual Carnot cycle between these two temperatures, okay? And I showed you last week how to do this calculation. We obtain 80%, okay? So this is a definition, an important definition that I'm presenting you for the first time. Or as we say, or thermodynamic efficiency, or first law efficiency is 54%, as we calculated here. But the maximum attainable efficiency is 80%. So when we divide these two numbers, 54 by 80, we obtain what we call a second law efficiency, or exergetic efficiency of 67.7%. And an observation, one reason for this loss of efficiency is the excessively high temperature of the exhaust gases, which still contain a significant amount of thermal energy. Okay, and that is exactly the reason why we tend to use combined cycles. We use, instead of, let me go back some slides, instead of rejecting this very hot air to the atmosphere, we can use this air as a heat source for another thermal cycle. Okay, that's what we're going to do. Okay, yeah, that's it. So we calculated the exit temperature, 461 degrees. Okay, so this amount of air, here we have low pressure. We have already expanded through the turbine, but we still have high temperature. So the idea is to recover some amount of this thermal energy with the help of a second thermal cycle. Okay, it's going to be a Rankine cycle. Okay, so we pass this air through we can call that a recuperator or a recovery boiler, okay, or a regenerator boiler. Okay, and we then heat water in a second thermal cycle here. Okay, so that's the idea of a combined cycle. I showed you that last week. Okay, but this week I'm not going to do the calculations. We did that last week. I just want to show you a comparison between open and closed cycle, or open cycle or single cycle and combined cycle. Okay, it's open because actually you send air to the atmosphere, the combustion gases to the atmosphere, so that's why it's called open. Okay, and combined cycle, which is the one I just showed you on the previous slide. Okay, so this table has a lot of comparisons. Okay, important parameters, including the economical ones. Okay, you see that I'm highlighting a few. The investment cost is higher, 20% higher. Why is that? Because you have more equipment. You have to buy more equipment. So that's why capex values are higher for the combined gas cycle. Okay, but the production cost drops dramatically. Okay, why is that? You see, from $200 per megawatt hour, generated megawatt hour, it drops to 55 to, let's say, $70 per megawatt generated. So you expend 20% more, but you get 66% more revenue. Okay, so you invest more, but you get more as income during the operation of your power plant. Okay, so that's why the tendency is to use combined cycle power plants, because the necessary investment is not that high and the revenues are considerably higher. Okay, I already did a technical economical analysis of these two power plants. Okay, open cycle and combined cycle. Okay, this is the cash flow of these two power plants. Okay, considering I'm not sure 30 years, the entire lifespan of the project. Okay, and these are the numbers, the technical economical parameters or econometric parameters, VPL, benefit cost, internal rate of return, and so on, comparing both. You see that the combined cycle is a lot better, okay, in all counts, in all comparisons. Okay, I have the spreadsheet. I can post a link to this spreadsheet on our Facebook page if you want. if you want to play with these numbers, okay, just to see. And I'm not going to have time today. I have still a lot of things to show you. But my intention was to build this spreadsheet with you from the scratch, okay? I'm not going to do that because I'm going to do that in some other occasion. And I'm going to broadcast through YouTube. So I'm going to post a link with the date and place where I'm going to show you this, okay? And for now, I'm going to post the link to this spreadsheet, and in order for you to have access to all these calculations, okay? Okay, let me just show you some power plants here in Brazil that is based on this principle. This is Governor Leonel Brizola's power plant. I say it's his because he was in charge at that time. Okay, this was built near Reduc, which is a petroleum refinery in Rio de Janeiro, actually Duque de Caxias. Okay, so you have this refinery is right beside. Okay, and well, it's a 1 gigawatt power plant, and part of it, I would say 1/3, actually is a combined cycle and steam. Okay, so it sells electricity to the petroleum refinery, which is right beside here. It sells electricity and also steam, because you need a lot of steam for processing petroleum. Okay. So instead of producing electricity from this amount of steam, it uses it as a heat carrier substance, okay, for the processes taking place at the refinery. Okay. The other part, the other 2/3 of this power plant is a combined cycle, a pure combined cycle. The Brighton cycle produces 330 megawatts. And the Rankine cycle, okay, produces 324 megawatts. Okay, so that's Governor Leonel Brizola power plant. This is an aerial view. You see, those are the pipes that supply steam to the refinery here. Okay, you get gas is obtained from Bacia de Campos and also from Bolivia, through the gas ball, gas pipeline, okay? And, well, that's it for now. And this is the regenerative boiler, okay? This unit here, I'm going to show you in some details, is this equipment here is exactly, I'm going back some slides, this is the regenerative boiler, okay? So it gets the combustion gases and put them into contact, thermal contact with water from the secondary cycle. Okay, so those are the regenerative boilers here. You see the chimneys here. Okay, and well, these boilers work roughly like this. As I'm showing you, have combustion gases coming from here, okay? You have the option, you can burn some fuel in order to increase the temperature here. That's interesting, okay? So hot gases are releasing heat from left to right, and then they are emitted to the atmosphere, okay? Water of the secondary cycle is pumped first. So here you have liquid water, low temperature. They absorb heat in 3 steps, okay? First, in the what we call economizers, okay? So you have cold water, actually compressed liquid. Then this water is heated to saturated liquid water. Okay, so you have, let me just draw a TS diagram here in order for you to understand what's happening with water. So this is the TS, temperature entropy of water. Okay, this point here, so it's well, this is the isobaric line. Okay, let me change color right now. So this point here is roughly here. Okay, then at the economizer you heat that to, okay, from here to here. So you have compressed liquid water. In the evaporator, you, as the name says, you evaporate, so you come here, okay? So this point is saturated heat, okay? If you need steam for your processes, you can obtain from here or not, okay? And in the superheaters, you heat the saturated steam to superheated steam. Okay, so this point here is the exit here. Okay, so the necessary heat is being supplied by the combustion gases from here to here. Okay, I just erase here and going back my point. So if you can see temperatures here. So water, this point here corresponds to this point here in the TS diagram. Okay, so it starts heating in the economizer. It heats to saturated liquid. Then it changes phases to saturated steam. So it changed phase, so the temperature remains constant here. The temperature is not changing here. Then it is superheated to the exit temperature here, okay, right here. Okay, when we follow the temperatures experimented by the combustion gases, supposing that we're burning a small amount of fuel in order to increase temperature, okay, so you have hot gases here, let's say 400 degrees, for instance. You heat it up to, let's say, 500 degrees, okay, then it starts to drop because it is continuously releasing heat in order to increase temperature of water. Okay, so that's how these regenerative boilers work. Okay, this is a more detailed, a more realistic picture of this type of equipment. Okay, just for your reference, for you to, in order to have an idea of the scale of the equipment, is relatively small. It's not very big. Okay, and that's it. I'm going to talk now about this was the gas cycle, how we make the calculations with a gas cycle, or as we call a Brighton cycle. But how do we obtain the fuel? Okay, so I'm focusing on obtaining gaseous fuel from organic residues. So I'm going to talk in a few words, actually, about how we can convert organic residues to biogas in order to use in a thermal power plant, as I showed you. Okay, so I showed you how the thermal cycle works, which generates electricity, and now I'm going to show you how we can obtain the necessary fuel. Okay, there's a lot of important details related to this conversion of organic residues to biogas. By residues, it doesn't have to be an actual residue. Okay, it can be, for instance, something that you buy. Okay. Well, let's go. So basically, you have organic residues. Okay, residues I can quote and unquote. Okay, residues here. It can be agricultural residues, municipal or industrial residues, and so on. You have a lot of especially oils and fats, for instance. Okay. This is a very efficient way of doing. Okay, the basic reaction is, or the basic process is anaerobic digestion. Okay, which actually involves several transformations or several types of chemical reactions: hydrolysis, generation of acids, acetogenesis, methanogenesis, and so on. I'm going to show you this in a little while. So when you digest these organic residues in a very deprived, in low quantities of oxygen, anaerobic, that's the meaning of this term here. When you pass through this process, you have gaseous products and solid and or liquid products. Okay, the gas products, the characteristics, I forgot to translate to English, but the point here is that the gas that you obtain here usually has a low heating value, okay, and it is also, let's say, a nasty gas. You cannot use it directly in a combustion machine, internal combustion engine, for instance. You have to treat this gas in order to purify, in order to remove nasty things that I'm going to show you in a little while. But anyway, you have most of the energies or most of the energy content of the residues end up here in the gas, okay, and which you can use to drive a thermal cycle, as I just showed you. Okay, so you get electricity by using an internal combustion engine or a gas turbine engine in a Brayton cycle, for instance. You also have rejected heat, which you can simply reject to the atmosphere. Okay. Well, about the solid and liquids that you get after anaerobic digestion, usually it's a very, very good fertilizer. Okay. The solid ones may be sold as fertilizer because they are very rich, but the liquid ones, let's say, they are poor with respect to the mass. Okay, every kilogram of liquid fertilizer contains only a small amount of fertilizer. 1 kilogram of solid residues contains almost, let's say, 1 kilogram of fertilizer. Okay, so usually the solid residues are sold and the liquid ones are used in local applications because they are too heavy or the concentration is too low. Okay, well, let's see what the composition of the gas that you get here. Okay, for comparison, let's consider natural gas. Yeah.
Professor, please, can you go back to the other slide?
This one?
Yes. Please, before you subject your organic residue to anaerobic digestion, do you need a form of pretreatment, or you just subject directly?
Yeah, well,
Do you need to pretreat your organic residue before digestion?
you may have some kind of pretreatment here, especially size reduction, depending on the sizes of these particles here. Okay, but usually no. I'm going to show you one that does not use, because it uses corn silage mixed with chicken manure. Okay, so usually pretreatment here is just reducing size or obtaining an homogeneous mixture. Someone is trying to call me here. Let me just... Okay. Okay. Did I answer your question? I'm going to show you in a few minutes how this is done.
Okay.
Okay.
Thank you.
Right. So I'm going to show you the composition of biogas from different sources, but I want to compare that with what we call our gold standard in terms of fuel, okay, which is natural gas, or almost pure methane. So as you see, and it is also, natural gas is also what we call an energy carrier, or what we call here in Brazil an energy vector. Okay? By that I mean this is a substance that contains a lot of energy, but also satisfy a number of properties in terms of viscosity and so on that define it in order for these substances to work properly in an internal combustion engine, for instance. Okay, so this is very important. Okay, so our gold standard is natural gas in terms of being an energy carrier or energy vector, as we say here in Brazil. Okay, so the composition is almost pure methane, okay, and other hydrocarbons, and very small amounts of carbon dioxide, nitrogens, and hydrogen sulfate. This is very important because this is one of those nasty components that I mentioned. Okay, but being almost 99% of energy-containing compounds, energy-rich compounds, the higher heating value is very, very high, 48 megajoules per kilogram. Just for you to have an idea, sugarcane bagasse is around, sugarcane bagasse with 50% moisture is less than 10 megajoules per kilogram. Okay, just for you to have an idea of these numbers. So it's very, very rich in terms of energy content, and for this reason, very, very pure, very rich in terms of energy content. So this is the prime fuel for large-scale thermoelectric power plants. Okay, so just as the one I showed you, Governador Leonel Brizola power plant. Okay, then I'm going to show you two sources of biogas. First, from anaerobic digestion. Okay, from vinasse, for instance, for, as I mentioned, chicken manure or pig manure. Okay, so let's just look at the composition. Instead of 90, you get 55% of methane. You get a lot of CO2, 35 against 0.7% in our gold standard. Okay, so and carbon dioxide, as you know, does not contain energy. Okay, you have some amount of nitrogen, comparable with natural gas, and you also have a lot of hydrosulfates. Okay, 500 ppms. This is very, very nasty in terms of using this gas directly in some kind of equipment. Why is that? You know, the combustion temperature, let me just go back a few slides. One that I have the combustion equation. Yeah, here. When you burn methane, you get water. Okay? What happens when you have water mixed with mixed with this hydrogen sulfates? Okay, what happens? You have sulfuric acid, okay, and this is going to destroy entirely your equipment. So this is not this is not directly applicable in an internal combustion engine or a turbine, a gas turbine. You have to do something in order to remove, especially hydrosulfates. Okay, you have to get rid of this. Okay, and for this reason, and also because the heating value is low, in 20 megajoules per kilogram, that is basically the influence of having 35% of CO2. So it's not a prime fuel for large-scale power plants, but you can use it in small-scale plants, especially in association with intermittent sources, as I showed you last class, okay, which can be wind or solar, photovoltaic energy, okay. Another important consideration is biogas from landfills, okay. I'm sure that you have seen, many of you have seen landfills. It's very common to see some flares installed in these landfills, and you can see the flame, the methane emitted from these landfills are being burned. And many people ask why we don't use this methane in order to generate electricity. Because of these reasons here. The heating value is very, very low because there's almost more carbon dioxide than methane, a lot of nitrogen, and a lot of hydrogen sulfates. Okay, so in order to use this biogas from landfills in an internal combustion engine or in a gas turbine, the amount of equipment that you have to have in order to get rid of these contaminants and to, let's say, increase a little bit the heating value, it's not economic. Okay, so usually this is not used for this type of application. So it's rarely used as fuel in electricity generation, but methane is a very, very important gas in terms of greenhouse effect. So you cannot emit it as methane. So it's better to burn, to transform methane to carbon dioxide, because methane is 72 times more absorbing. The greenhouse effect of methane is 72 times higher than the greenhouse effects of CO2. So you burn methane in order to emit CO2 in order to avoid emitting methane. Okay? So,
Teacher,
yeah, go.
I have a question about what is the difference in the biogas from anaerobic digestion and the biogas from landfills, but the process, why is the difference? What is
Yeah. Yeah, I think my next slides, I'm going to show you the steps which compose. Both are anaerobic digestion, actually. Okay, what changes is the feedstock. Okay, because here, depending on what type of residues that you have. For instance, let me ask you with my slide here. I'm just going to do something here. Okay, if you allow me, I'm going to let me do something here. I'm going to just going to amplify this graph here. Increase. Okay. Nope. That's okay. Okay. So. What changes actually is the feedstock. Now, this graph shows the amount of natural gas or biogas that you obtain from 1 ton of feedstock. So you see, for instance, cow manure, pig manure, and chicken manure are very bad fuels or very bad feedstock for natural gas production. Okay, so chicken manure is interesting, but pig and cow it's not very good. Okay, and fats, greases, and oils, bakery wastes, food scraps, and so on, and corn silage. Okay, corn silage. You get a lot of natural gas from this kind of waste. So the chemical or biochemical reactions are more or less the same, but as the composition of the feedstock changes a lot from organic residues, as I show you here, or from municipal residues, they change a lot. So the composition of the products change a lot. Okay. Okay. Are you satisfied with my answer? Okay, okay. So, coming back here, both are anaerobic digestion, but well, usually this is from those types of residues, and landfills you use municipal garbage actually, okay, that you try to ferment. I also want to say that this is not my area of expertise, okay, so I may be wrong in some points, but I believe in the whole I'm correct, okay, but if I say something wrong, please correct me. There is no problem, okay? I know that it may be the specialty of one of you guys, and if I say something wrong, please correct me. And, well, I can learn from your correction. Okay, so let's take a look on these reactions. So the idea is that you have some kind of feedstock that you're going to anaerobically digest, okay, which actually is a degradation of these organic compounds through a series of fermentative processes occurring in an oxygen-deprived atmosphere. Okay, anaerobic stands for oxygen-deprived atmosphere. Okay, and these reactions involve microorganisms. Okay, so you have some kind of feedstock which can be, as I showed you last week, a mixture of corn silage and chicken manure. Actually, you use corn silage in order to increase the energy content of the obtained biogas. Okay, so the idea is that you have this raw material, and you first start, and these raw materials have, let's say, carbohydrates, corn silage, for instance, lipids and proteins. Okay, the first layer of reactions is hydrolysis. So carbohydrates are transformed to sugars; they are separated. Okay, lipids to fatty acids and proteins to amino acids. Okay, so there's several layers of reactions, and every layer involves different types of microorganisms. Okay, a second is acid generation. So sugars and fatty acids generates carbonic acids and alcohols. Okay, on the other side, you already have generation of gases, H2, for instance. H2 is a valuable energy carrier product. You can stop reaction here and use only H2. But you also have CO2, okay, because some of your microorganisms are breathing, actually, instead of fermenting. Okay, you have ammonia, and you also have sulfates, which are those nasty components that you have to get rid of in order to avoid having sulfuric acid in your system. Okay, then another layer, formation of acetogenesis. Okay, H2, acetic acids and carbon dioxide. Okay, and then generation of methane. So you have methane and CO2. Okay, as I said, this is a very simplistic view of this several or layered reaction, but the idea is to show you the complexity of this process, because you have different microorganisms living and striving in this reaction. So it's very, very difficult to control, and that's why when you change composition, the initial composition, the final compositions may change a lot. Okay, that's the reason why changing the input feedstock, the feedstock here, changes the relative amounts of carbohydrates, lipids, and proteins, and the consequence is that the composition of your final products may change a lot. Okay, well, that's I don't know if you remember, that's from last week's class. That's the project that power plant, the integrated power plant near Berlin. I don't know if you remember. Yeah.
Professor,
Yeah, go on.
I have a question. In that anaerobic digestion process, do you generate waste or is it only sulfates?
Sorry, I didn't.
What are the other wastes generated in this process, anaerobic digestion?
Oh, this is a generic picture of the process. It can be, as I'm showing here, it can be food scraps, for instance, or cow manure. The idea is this kind of residue will pass through these several layers of biochemical reaction. Okay? This, as I said, this is a very simplistic view, but the idea is to show you that every step, every layer is controlled, must be strictly controlled. Otherwise, you can have very different types of products in the end process. Okay, but that's the maximum that I can explain to you, because, as I said, that's not my expertise. Okay. Okay, so moving on, that's from last week's class. That was that integrated power plant near Berlin. So it was integrating photovoltaic with biogas generation, and the feedstock was chicken manure and corn silage. Okay, so it's a mixture of corn silage and chicken manure. And the idea is that you increase the energy content of chicken manure with a small amount of corn silage, 30% of corn silage. So all those layers of reactions, these several layers here, occur in these two reactors. Okay, that's why you have 2 or sometimes 3 reactors in order to better control, okay, this cascading here. Okay, but what I want to show you today is what can you do in order to purify those biogases that you obtain here at this point here. Because, as I said, it contains sulfates, which are nasty, and, well, several other things. So I'm going to elaborate to show you what we call a gas scrubbing process or a gas purification process. It's something like that. It's like a shower. Okay, so you have raw biogas coming in here. Okay, and this gas goes upwards, and water comes from the top and flows downwards. Okay. So the idea is that you have, well, gas is already a gas, but water is pulverized in very small droplets so that the interfacial area between water and gas is very high value, okay? So it can exchange, it can chemically react very easily, okay? So you have, you add compounds, NaOH, H2O2, and other types of chemicals in order to, for instance, remove sulfates from the gas, okay, or even CO2. Okay, so the idea is that when you wash, that's the idea. A gas scrubber is like washing gas with water droplets. So here, theoretically, you have purified and enriched in terms of energy a gas that you can send, going back one slide, to your machine, in this case internal combustion engine. Okay, you could, at this point, you could compress this gas and sell this gas as a vehicular fuel. This is being done. For instance, I know that São Martinho sugar plant intends to do that. They already ferment, actually they ferment vinasse, they produce methane, but they are simply only burning methane in order to produce heat. Okay, their intention is to install this kind of equipment and also a compression system here in order to sell this as a fuel for cars. Okay, so that's the gas scrubbing process. Let me see the time. Yeah, I must hurry up a little bit because I have to talk now about biomass. The use of biomass as a thermal source in power plants. Okay, so I'm going to start by talking about what I call the agro-industrial system. Okay, what I call an agro-industrial system is a system of producing and processing biomass, which encompasses, let's say, three layers or three gears, we could say like that. Okay, so production, logistics, and processing. Okay, so physically, this system, you have an industrial plant here, which will process the crops that are harvested in the fields, okay? Grown and harvested in the fields. So, just for reasoning, suppose that the area around the industrial unit is a circle, okay, of radius r. You're going to, I want you to reason with me, okay? Okay. This is an important picture. I'm going to come back to it in a few slides. But the idea is that once you spend energy for harvesting, for all soil operations, for instance, you have to plow, you have to prepare the soil in order to grow these plants. But you also have agricultural operations associated with harvesting. For instance, you have harvesting machine. If you, in the case of sugar cane or corn, if you want to use the straw, you have, for instance, steading operation, baling operation. You have several. Actually, you have 4 or 5 operations here associated with recovery of straw. Okay, so the idea here is that you have some kind of agricultural feedstock which are rich and easy to process, like corn grains or sucrose or sugarcane juice. Okay, but you also have agricultural feedstock which are hard to process. You can think of this bales, okay? Lignocellulosic material. I don't like the term residue because it's not actually a residue, okay? So in terms of the processing, in a historical perspective, the first ones are the ones that we call first generation. 1G stands for first generation. So you get this feedstock, let's say corn grains, just for reasoning. You can have some operations here in terms of preparation. In sugarcane, for instance, extraction. You have to extract sugarcane juice from bagasse. Okay, and for that you have to reduce size. You have to have a certain proportion of open cells and so on. Okay, and then you have biochemical reaction, which we're labeling first generation. This is basically fermentation. Okay, so you can do that in order to produce fuel, ethanol, or chemicals. Okay, so this is the first and well-known processing pathway. Okay, but it's applicable only to those parts, to those mild parts of the plant. Okay. The second pathway is for the hard parts of the plant, the hards in terms of processing, and this can be a biochemical also, we call that second generation pathway, but also it can be a thermochemical pathway. Okay, and this, let me just write down some numbers already. This thermochemical pathway actually is very, very old. We have at least 200 years in terms of accumulated experience in processing through combustion, pyrolysis, and so on. I'm going to talk about the last slides of this class. I'm going to talk about this thermochemical pathway. Okay. Another one that is being deployed right now is the second generation pathway, which is basically fermentation of this type of material. Okay. In order to ferment, you have to deconstruct that. You have to deconstruct the lignocellulosic structures in order to release the sugars contained in this type of substance. Okay, I'm sure you are aware of that. In terms of histories, I mentioned that we have 200 years in terms of accumulated experience here. I would say that here in Brazil, we have around 50 years of experience here in Brazil. Throughout the world, even less. Okay, this first generation pathway, and here I would say we have less than 10 years here. Okay, so that's one important problem, because you have alternatives here, and some pathways are more developed, more mature in terms of technology than others. So that's one point that I'm going to highlight in a few moments. But just to explain you one particular point related to the scale of this agro-industrial system. Okay, so just to remind, our industrial or agro-industrial system is composed of a plantation area, okay, of radius r. So r is this distance from here to here. Okay. In the center, we have the industrial unit, and we also have logistic operations in order to transport the crops from the fields to the processing units. Okay? So let's reason in terms of economics. Okay? So what about our revenues? The revenues that we can obtain from this system. Okay? Well, the revenues are proportional to the amount of biomass that you have for processing, okay? And this amount is proportional to the plantation area, okay? And the plantation area is proportional to R squared, okay? To the area of the plantation. So the amount of revenues increases with the square of the scale factor. R, in fact, is our scale factor. Okay. Let's think about the expenses. Okay. The expenses are mostly related to not field operation, but field operations. Okay. And field operations, the cost is proportional to what? Well, it's proportional to the amount of biomass. Okay, so it's proportional to the area, but it's also proportional, I'm going back 2 or 3 slides, it's proportional to the distance that you have to travel from the fields to the industrial unit. Okay, so it's proportional to the area, or square, times the distance. R squared times R, so it's proportional to R to the third power. Okay, so the behavior of these curves are more or less like this. Well, it's not starting at 0 because you have fixed costs. Okay, and the behavior is this. So this shows you that you have viability limits, a lower viability limit, and a higher viability limit, which is defined. Those limits are defined or this range of viability is defined when you have more revenues than expenses. So your operation is profitable, okay? This is a very important concept because you see, scale is everything. You have to set your project within this viability limit. We know this already for the sugarcane sector, for the first generation sugarcane sector in Brazil. We have statistics on that. So this histogram actually is a histogram of all state of São Paulo's sugar mills, and this is the plantation area. So you see that the majority processes 30,000 hectares, and there are some with a lot more, but they have better technologies, especially related to logistics. So when you have good logistics, these red curves increases slowly, so your viability limit it's larger. Okay, so you can have larger operations, but the majority here in São Paulo processes 30,000 hectares, which corresponds in terms of processing rate of 500 tons of sugarcane per hour. Okay, TSC means tons of sugarcane per hour. Okay, and during roughly 200 days a year. Okay, so this is the size of the plantation area, typical size of the plantation area, and this is the typical processing rate, okay, of an industrial, agro-industrial sugarcane system. Okay, depending on the added value of your product, depending if it's sugarcane or other type of agricultural product, this viability limit, which for sugarcane is in average 20 kilometers, may increase a lot. For instance, you can produce acacia, with sorry, miss, acacia, which is a kind of a tree, and from acacia you can extract and produce tannins. Oops, tannins. Okay, which tannins are used for leather processing, for producing adhesives and other chemical compounds. Okay, so it's tannin has a higher commercial value than ethanol, and for the case of this agro-industrial system, the average radius is not 20 kilometers, it's 100 kilometers. Okay, km. Okay, so depending on the added value of the products, if it's ethanol or tannin, your limits are different. Okay, and this result here is for sugarcane here in the state of São Paulo. Okay, and as I mentioned, you can have larger operation, but especially with increased logistic efficiency. Okay. So that's this is a theoretical reasoning. Okay, this is statistics, and this is what this industry became. Okay, actually, when I mentioned, let me go back some slides. When I mentioned that we have 50 years of experience, when I say we, I mean here in Brazil, the sugarcane industry here in Brazil has more or less 50 years of experience, okay, and it resulted in this kind of system. So it's in average 30,000 hectares of plantation area, okay. This corresponds to processing 500 tons per hour, 24 hours a day during 200 days a year, okay? And in order to process this flow rate, you have a sugar mill which is typically something like this, okay, of this size, I mean. Okay, this is Usina Vertente, if I'm not wrong, in the city of Guaraci, okay, Minas Gerais, if I'm not wrong. Please correct me if I'm wrong. So, well, in this case you have a diffuser. Sugarcane arrives here. Here you extract sugarcane juice from fiber material, okay. Juice goes to the sugar factory or to ethanol factory here, and bagasse goes to the boiler. Bagasse is burned, generates steam, generates electricity. You can use steam as a heat source for all processes here, and also electricity. And when you do the calculations, by processing 500 tons of sugarcane, so this is the amount of sugarcane that you have to process. For instance, in terms of logistics, this means unloading one wagon like this every 5 minutes. So it's a very, very significant logistic problem, okay? When you process this amount of biomass, I mean at this rate, okay, you produce, you're able to produce 35 tons per hour of sugar or 42 cubic meters per hour of ethanol, okay, from the sugar cane juice. And from bagasse, you can export 50 megawatts, okay. This is surplus, okay. All electricity necessary for the processes are already accounted. So 50 megawatts is surplus electricity that you can sell on the grid, okay. In terms of inputs and outputs, well, let's see. You need 1,000 tons per hour. Sorry, this is wrong. This is 1,000 kilograms per hour of water. You have to import water. Okay, this is still a bad result, a bad number about this system. Okay, you also emit 2 tons per hour of CO2 for fermentation. So the fermenters here will emit 2 tons of CO2, and the boiler stack will emit 100 tons per hour of CO2, roughly speaking. Okay. These numbers are important in terms of carbon capture. I'm going to show you in a few moments, okay? Because this carbon here and this one here actually was in the atmosphere and was captured by the photosynthetic reaction of these leaves, okay? So this CO2 is going back to the atmosphere, but it was captured by photosynthesis, okay? You also produce 1 to 10 tons per hour of solid residues. They are very rich in terms of nutrients, and also 500 cubic meters per hour of vinasse. And these two residues are very, very rich in terms of nutrients, nitrogen, potassium, and NPK, okay? Looking from the field, from the plantation side, an important issue is that these plants are removing, obviously, sunlight, water, and CO2 from the atmosphere. There's no problem with this, okay? But this is very important. These plants are removing 1 ton per hour of nutrients. So if you don't do nothing, in 5 years, and 4 or 5 years, this is going to become a desert. So you have to send back the nutrients. You have to take it back to the fields in order to maintain productivity. Okay, so that's why logistics is not only in terms of bringing the crop from the fields to the factory, but also sending nutrients from the factory or from the store, if you bought that, and applying that on the fields. Okay, so the logistic problem goes both ways. Okay, and in 50 years of operation, the maturity level is already at 9, so you have what we possibility of this type of contracts, as we say, turnkey contracts. So it's already a commodity. Okay, all this equipment is very well known. Even the price. So the price will cost around $200 million. Let's say 3 or 4 commercial jet airplanes. That's the cost of a sugar mill, an average sugar mill. Okay, and well, this is actually here, this pathway here. Okay, I want to show you during this course and during this particular classes, this pathway and also this pathway. This one is very old and very efficient already, actually. Okay. So let me go on, and yeah, the importance of these sugar mills is not only in terms of producing sugar, ethanol, and even chemicals, but as I mentioned in our first class, in terms of capturing CO2 from the atmosphere through photosynthesis, and by sending it by fixing it, by storing it in the undergrounds. Okay, in these bedrocks here. Okay, this I showed you in the first in our first class about climate change. Okay, and sorry for that. And the idea is that you have to adapt this industrial process in order to produce supercritical CO2 in order to be able to inject in the underground. Okay, I'm going to elaborate on that today. I'm going to show you how this can be done. Okay, and I'm going to show you some results of an exergy analysis of this process. Okay, yeah. Well, and just to complete, this is another slide from that presentation. The idea is that these producers, well, they start, let's say, instead of emitting CO2 here in the stack, you capture this, you transform that in terms of a CO2 carrier or CO2 vector, and then you inject that in an injection well. Okay? Yeah, I mentioned it. So let's see how the process, how a typical sugarcane mill could be retrofitted to a CCS machine, carbon capture and storage machine. So this is a typical first generation sugar mill. Okay, you have sugarcane. The trucks are arriving here at that rate, 500 tons per hour. You have mechanical processing, size reduction, separation, fibers from straw. Straw you can burn directly in the boiler as a fuel for your boiler. It has a low moisture content, so it's very good. Okay, from the rest you can extract juice. So juice, you can produce sugar, or you can ferment and produce ethanol. Okay, the residues is vinasse. You have bagasse here with a high humidity content. You dewater in order to be able to burn that in a boiler. Okay, that and produce steam, high temperature, high pressure. Okay, so it fuels a thermal cycle. Okay, so here you have a Rankine cycle. The surplus exergy or electricity can be sold to the grid, and you have energy for your processes and also heat for your processes. Okay, electricity and heat. Yeah, go ahead.
I have a question here regarding sugar production, ethanol production. I would like to understand from these two pathways which will be the most efficient Because I imagine that it would be efficient to produce sugar and just with the centrifugation, molasses, produce ethanol.
Mhm.
And but I don't know whether that is sufficient to produce enough ethanol, or I would like to understand more and see what in the case of Brazil, which pathway is the most common.
Uh-huh. Yeah, well, actually, it depends. It always depends on the price of sugar and ethanol in the markets, okay? So, and also, well, I would say, depending on your country. Here in Brazil, most of our sugar mills are capable of producing ethanol or sugar, or 50-50 or 30-70%, okay? So this amount, that's why I put a valve here. The idea is that you control the amount of sugar and the amount of ethanol that is being produced, that are being produced, the amount of sugar and the amount of ethanol, depending on the prices, okay? So you can change that during the year or from one year to another year, depending on the prices. I know in the recent past, sugar, because United States and especially in India, they had problems. So the price of sugar in the international market was very high. So they were diverting the production they were diverting sugarcane juice to produce sugar. And also because the price of ethanol here in Brazil was fixed, because the price of gasoline was fixed. Okay? So this was a scenario, let's say 5 years ago. Okay? A scenario 5 years ago. And this changes during time.
If they produce sugar, they can also produce ethanol with the molasses.
Yeah, they can. And that's what I was going to say. In some countries, like in South Africa or India, they don't have this ethanol facilities here, so they can only produce ethanol from molasses. They are not capable of producing high quantities of ethanol. So yeah, they just ferment molasses to produce ethanol, because this is a very difficult to ferment compound, because it's not sucrose, it's fructose and other more complex sugars. Okay, so it's not very easy to ferment that. Actually, as a nutrient, is very good. Okay, for even for human consumption. I don't know if you have tasted that. Molasses is a very rich food. Okay, but the demand is not that high. Okay. Okay. Okay.
Yeah, thank you.
So this is a typical sugarcane mill here in Brazil, and I want to show you what type of changes that we have to need to implement in order to transform that to a CCS machine. Okay. Well, first you have where are your emissions? So CO2 is being emitted here on the boiler's stack, okay? CO2 is being emitted here in fermentation process, so here is 100 tons per hour, 2 tons per hour, okay? But also, depending on what you do with vinasse, you also have emission of CO2. For instance, if you apply vinasse in the fields, in order to do what we call here in Brazil ferti-irrigation, vinasse is very rich. It's not as rich as sugarcane juice, but it still has a lot of energy. So it's going to ferment in the soil, and it will also produce CO2. Okay. So the idea is to, instead of emitting this CO2s, which came from the atmosphere because it was fixed by the plant, okay, the idea is to capture that. Okay, we're going to get rid of the stack and so on. So what do we need to do? Well, first we can add a second generation processing pathway, so we can divert some amount of straw and or some amount of bagasse in order to produce sugars capable of being fermented. Okay, so the idea is to pre-treat and hydrolyze this material and to ferment the fermentable components. What's not fermentable, especially lignin, has a very high caloric power, okay, caloric content. So it's very interesting to burn it, simply to burn it. Okay. Actually, it's comparable to natural gas. Okay, celluloses and hemicelluloses is something around, let's say, roughly 10 megajoules per kilogram, and lignin is something around, I would say, 18 megajoules per kilogram. So you see, it has a very high energy content. It's very, I would say, impossible to ferment, so you better burn it to produce heat. Okay, so that's the conventional, that's the first step in changing the process in order to generate that CCS machine. Okay, just a comment, I can send you the slides if you want. Okay, no problem. I think I already did that. I posted a link on our Facebook page. Somebody asked me for the slides. I already posted all the slides for all the classes during this semester. Okay, you have access to that. Well, the second step now is you have to do something with vinasse because you don't want to emit that. So the idea is to digest it. Okay, one interesting consequence is that you produce fertilizer. Well, you can, so you produce methane here, CH4, that you have to process in order to send this methane to your boiler. Okay, so you're not emitting any more CO2 from vinasse. Okay, well, now we have to change the boiler. Okay. The problem here is that our boiler is using air to burn our fuels, in the plural now, okay? And it's emitting, let's say, roughly speaking, N2, CO2, and H2O, okay? The problem is that, well, H2O is very easy to get rid, but N2, it's very complicated because you have very big amounts of N2. So what we can do is, instead of using air here, we are going to use pure oxygen, okay? Pure oxygen, okay? In order to do what we call an oxy-fuel combustion process or an oxy-fuel boiler, okay? Well, let's see this in detail. So you need O2. Remember, I'm going back one slide. We were processing through anaerobic digestion, then scrubbing. You can change that because if you know that you produce O2, you can, well, still digest that. And the remaining liquid, which were, I don't know if you remember, fertilizers, okay? You can use that to produce microalgae. Okay, I'm sure that you read already about biodiesel from microalgae, so you still can produce some biodiesel here. It's a very small quantity. Don't bother, but it's possible. Okay, the most important here is the ability to produce O2. Okay, so. And I'm going to talk about why this is important in a minute. So you need O2 for your oxy-fuel process. You can obtain O2 from vinasse, okay? But that's not enough, so you have to get that from the atmosphere. So you need a separation process which takes air, separates oxygen, and emits N2. This is almost pure N2, so this may have a commercial value, okay? Well, that's okay. So you don't have N2 anymore because it's being emitted here. So when you burn fuels here, here, and here with pure oxygen, you're going to have CO2 and water. Okay? What you can do now, well, H2O, it's very important and easy to separate. You just cool that a little bit. So you dewater these gases, you get liquid water here. And remember, I'm going back some slides. Our process it has a negative water balance. So recovering some amount of water is very interesting. Actually, we are able to recover more water than we need. So when you do that, you're going to become positive in terms of water balance. This is very interesting. Okay. And where was I? Yeah. And after dewatering these gases, you have pure CO2 that you can compress in order to produce supercritical CO2. Okay? For that, you need a certain amount of energy. Okay? And the whole idea is that this amount here is smaller than the remaining surplus energy. Okay? I'm going to show you all the calculations, all the results in a moment. And I think our last class is all the complex calculations. If you're interested in this subject, and I can send you, actually there are a 6-hour video in which I describe in greater detail all the calculations, okay? For the process that I'm going to show. So I'm going to show you in more details this particular process here. But it's very important that you understand what is being done here. Okay. So I'm going to focus on this process here. Let me control my time. Well, so this is a typical oxy-fuel boiler. Well, let me go back one slide. An oxy-fuel boiler is not a new technology as far as coal is your fuel. Okay, so you already have large-scale oxy-fuel boilers. This is 1 gigawatts. 1 gigawatts coal boiler. Okay, so this is a mature technology for coal. But it's not commercial for biomass, or I would say biomasses. Okay, so this is an interesting opportunity, I would say, because coal is virtually free of water, of humidity. Okay, and biomasses they all have humidity, some amount of humidity, and this changes a lot the technology that you have to apply in your process. Okay, so this already exists, oxy-fuel boiler for coal. Okay, but it does not exist for biomass. And what I'm going to show you right now is because, as I said, coal virtually has no water, no humidity, and biomass typically 50 to 70% humidity. You can figure, let's say, sugarcane bagasse after the last mill, it is around 50% humidity. Okay, so humidity is a problem as far as burning. You're concerned with the burning operation, but as I'm going to show you right now, it's very interesting in terms of how you control the combustion temperature. Okay, now. What I showed you in the beginning of this class, the calculation of the combustion temperature, will combine what I'm showing you right now. Okay, so let's see the equipment, how it is. Okay, so this is the boiler. Let me go back to my pointer. This is the boiler. Okay, here is biomass as a carbon source, and remember that it always has humidity. 50%, let's say. Okay, so you burn biomass with pure oxygen. Okay, that you extract from air. So this diagram actually represents more or less the physical installation. So this is a compressor. It's getting air, compressing, and passing this compressed air through a membrane separator. So you get oxygen on the outside and nitrogen here. Okay, so this is a very new, I would say, new and efficient separation technology. Why I'm saying that it is efficient? Because it demands low amounts of energy. So, okay, this red arrow here, you can imagine this is electricity, okay, that you're taking from this electricity bus here, okay? So, this red arrow actually is what we call electricity bus, okay? So, if you need electricity, you take it from this bus, okay? Okay, so you burn biomass with oxygen, produce heat. Heat produce superheated steam here at this point, okay? Superheated steam expands in a turbine. This is a two-stage thermodynamic cycle. So you produce electricity that you inject in the exergy bus here, okay? Then you have expanded steam. You reheat this, you expand again, produce electricity, inject that in the electricity bus, okay? Okay, so you expand, and then you reject the remaining heat, and the cycle goes on, okay? If you need heat for your processes, for instance, in order to heat water to extract sugar in the diffuser, to extract sugarcane juice, okay? You drain a certain amount of heat here and send that to the process, okay? Well, the thermodynamic cycle is a Rankine cycle. We're not going to do any calculations today, but just to show you, okay? So it's a Rankine with reheating, okay, as it is shown here, okay? So virtually, you have, if it's an oxy-fuel combustion, at this point here, you have CO2 and H2O. You don't have nitrogen because you're using O2. You're not using air, which contains a lot of, more than 70% of nitrogen, okay? So you have CO2 and water. You have to get rid of water first, for many reasons, and also because the overall water balance is negative, okay? The equation, the combustion equation, just to give you some numbers, the classical combustion equation with air, okay, this is more or less, this is the average chemical formula of sugarcane bagasse, okay? This is all the stoichiometric calculations are already here, okay, or the results. So you need 100 moles of air per mole of fiber, okay? And you produce, as you see, a lot of nitrogen. When you do this with pure oxygen, okay, you don't have nitrogen, okay? Well, so we're going to have to get rid of the water. We want to recycle water in the process, and we also need to compress CO2 in order to transform it to supercritical CO2, okay? Well, the next step then is, well, you can remove solid particles, ashes, and so on. This is just a detail in this diagram here. But so here you have pure CO2 and water. You can cool that to 7 degrees. Typically, the temperature here is 170 degrees here. Okay, this is a typical temperature. If you cool that to 70 degrees, water is going to condense. Okay, so you can recover and recycle water in the process. And I'm going to show you the calculations. Actually, you can export water because you recover more water than you need for all the processes that were shown in the previous slides. Okay, so virtually here you have pure CO2. Okay, pure CO2. What you need to do now is to compress that. Okay, I was forgetting to say something. Okay, here you have virtually pure CO2, but as I said during the beginning in the first calculations, you need to do something here because the temperature here is going to rise above 3,000 degrees here, right here. Okay, in a traditional oxy-fuel boiler, what they do is to recycle CO2. So you get some amount of CO2, which is cold here, typically, I don't know, 60 degrees. You inject CO2 here, and this recycled CO2 plays the role of N2 in a traditional boiler. Okay, I'm going to show you that with biomass you don't have to do that because it already have humidity. So the idea is that you by measuring the temperature, the combustion temperature, okay, let's say that your boiler needs 700 degrees. If you don't control the temperature, it's going to rise to 3,000 degrees. Okay, so you measure the actual temperature, and depending if it's above the set point, you inject water that you get from this recycled water, okay, in order to control the combustion temperature. Okay, and this is very, very efficient because you inject liquid water. Okay, and water is going to change from liquid to gas and absorbs a lot of heat, latent heat, and then is going to heat up to the set point temperature. Okay, and this is very efficient, much more efficient than recycling CO2. Okay, this is very, very interesting. This is a coincidence actually, but it's a very interesting. I mean, the boiler is going to become much simpler and smaller because you don't have to recycle a gas in order to control the temperature. You recycle water, liquid water actually. Okay, so you inject liquid water here, you recover steam here, you recover water in the gaseous phase. Okay, so it's very efficient. Well, the next step, as I was saying, is to compress CO2. So it's simple. You have pure CO2 at this point, so you have to pass that through a series of compression and cooling operations. And well, at this point here, you virtually have pure CO2 in some supercritical region. In practice, you always have some non-condensables, which can be CO2, which can be nitrogen, some ppms of nitrogen, or some other non-condensables that you can pass that through a degasser and emit that. Okay, so here virtually you can have very small amounts of N2 because, well, your separation process is not perfect. Let's say like that. Okay, but these are very small amounts that you don't have to worry. Okay, so the main concern or the main advantage here is that you don't have to recycle CO2 in order to control the temperature here. Okay, and since you are recycling, yeah, go on.
I have a question about the supercritical CO2. If you leave this supercritical CO2 and normally pressure, you know, this volatilize, this product volatilize or not?
Yeah.
Stay with.
Yeah. Typically, let me get my pen. The pressure here is greater than 70 bar typically. So this is average pressure actually, but the temperature is low. So above, let's say, sorry, 40 degrees. Okay. So if the pressure decreases, it's going to become, depending on the pair of numbers, pressure and temperature, it may become a gas or it may become a liquid. Okay, but it's not going to be a supercritical fluid anymore. Okay, it depends. And I don't know if you remember why supercritical, because it's a fluid with a very high density, so it's a good CO2 carrier and a very, very small viscosity. So it's very easy to inject that in the bedrock. Okay, so it will flow through the interstices of the rock very easily. Okay, so you don't spend power in order to pump CO2 in these rocks, into these rocks. Okay? Okay.
Okay, thank you.
Okay, so let me move on. Yeah, and this is the overall exergy balance. This is the subject of our last class. Okay, and if you're not, since you're not familiar, I suppose, with the concept of exergy, no problem. Well, this is the subject of our next class. And actually, it's very simple. You can replace in your minds the word exergy, you replace it with electricity. Okay? So I simply could say, this is the electricity balance of this process. Okay? And, well, so here are the numbers. E stands for electricity or exergy, as you wish. So you can see the numbers here. So let's see here. The electricity content of your fuel is 374 megawatts, and this is processing, well, I don't remember the amount of mass that is being processed, but this is relative to this electricity or exergy content, okay? And, well, every input and output contains some amount of exergy, okay? And when you do all the calculations, okay, you see that you still have a positive surplus. Okay, so this means that, I'm going back one slide, that if the surplus here is positive, this means that you can still inject electricity into the grid and obtain revenue with that. Okay, and well, as you're going to see, this result actually is a very conservative result. It was obtained with a very, very simple thermal cycle, a very inefficient one actually, okay? And, well, with only 2 compressors. So this is a very conservative scenario. And even though we still have positive surplus, okay? So the conclusion here is very important. The conclusion is that you can transform this sugarcane or this oxy-fuel boiler into a CCS machine, provided that your carbon source is from biomass, from which captures CO2 from the atmosphere. So the conclusion is that you can transform that to a CCS machine and still export electricity. Okay, I'm going to show you all the calculations, if I'm not wrong, in our last class. Okay, okay. Let me just, I have a few moments before my time is gone. I want to talk very quickly about thermochemical routes. Okay, processing. Okay. Remember, I showed you this slide a few moments ago. I was talking about the different processing pathways that we have in order to transform biomass into something useful, okay? And I said that this pathway here is very old and very mature, because it has been tested for many, many years, okay? So I'm going to show you some numbers related to this. And before getting into detail. So this is a compilation of actually liquid biofuels industrial units. This is compiled by the International Energy Agency. The test 39 is focused on bioenergy. So this is, I obtained this from their site, and it's a dynamic map. You can ask for specific items. So here are all the installations related to producing biofuel from biomass. So I'm going back one slide. So every unit that do this process some kind of agricultural feedstock in order to produce fuel, no matter if it's 1G, 2G, or thermochemical, okay, is listed here, okay? So all kinds of technologies, gasification, fast pyrolysis, hydrothermal, and so on, okay? They are all present. All levels of technological maturity, okay? And all kinds of status, planned, under construction, already operation, and so on, okay? So just for you to see the number of dots around the world, okay? Actually, I said something wrong. It's not considering first generation units. So here you have second generation and thermochemical units, okay, except first generation units, okay? So that's it. When we filter that, if we uncheck these boxes in order, for instance, to look at only the operational ones, you see the number is drastically reduced, okay? But still in all levels of technological maturity and all kinds of technologies. So let's filter a little more. Let's consider only the more mature ones. TRL 8 and 9 are both commercial plants, okay? TRL 9 means that you have more than one unit of the same configuration running for a certain period of time, okay? So when you filter TRL 8 and 9, you have even less units. And when you filter, because you see, I filter here fermentation, hydrothermal, and other technologies. Hydrothermal here means that you're converting oily residues and fatty residues through hydrothermal processing. So it's still a thermochemical pathway, okay? So there are some thermochemical plants here. When you filter only fermentation, that's second G, pure second G, so you have only these units. So here, only the commercial ones through fermentation, second generation fermentation, and operational. So you see, we can count 1, 2, this is Grambio, this is Raizen, 3, 4, 5, 6, 7, 8, 9, 10. 10 units, roughly speaking, 10 units, okay? So, as far as the second generation pathway is concerned, we have, let's say, roughly speaking, 10 units of considerable scale operating in the world. Just for you to have an idea of how that compares to the thermochemical pathway, which is a lot, let's say, older than this technology. Here you have a picture of all oil refineries in the world. Okay, so these are actually oil and or gas refineries in the world. So you see, the scale is much huge, much bigger than the scale. It's been operating for more than 100 years, and the thermochemical processing pathway was born in this type of industry. So it's very hard to compete with this kind of technology. The most important disadvantage of this sector is that it's completely based on a non-renewable source, which is petroleum or coal or something like that, or gas. Okay, it's non-renewable. But when we talk about displacing gasoline, for instance, and replacing it by ethanol, bioethanol, well, that's the scenario. That's the scenario that's going to be that all sugar or biomass plants have to occupy. You have to erase all these red points and turn that into, let's say, green points. But that's the scale of the problem, just for you to have an idea. Okay? So it's a very, I would say, big problem. It's going to have to happen because virtually someday we're not going to have any more petroleum or coal or gas. Yeah? But it's still a very huge task to be done. Okay? Let's just take a look very quickly in these pathways. What is this thermochemical pathway in terms of the reaction and processes? Because we always talk about combustion. Combustion is one type of thermochemical process. There are other types. Okay? Let me just show you what we call thermochemical decomposition. Okay, when you heat some kind of material, depending if you have oxygen or you have not oxygen, different types of reactions will occur. Obviously, when you have oxygen, you have a combustion reaction. Okay, and well, the temperatures, the practical temperatures, range between 700 and 1,400 degrees. Low pressures. Around the atmospheric pressure. You don't need catalyzers in order to catalyze the reaction. And if you want to recover water, you have to dewater the products, the gaseous products. Okay? Okay, so this is very well known. I want to talk a little bit about the other chemical decomposition techniques which occur in the absence of oxygen. Okay? So depending on the, well, let's look at this diagram here first, and then I'm going to talk about this chart here. Okay, if you take biomass or any material actually which has some amount of humidity, if you heat this, you start increasing the temperature of this material in the absence of oxygen, something is going to happen. Okay, in the first, so it's an oxide. Okay, and you may have some water associated with the humidity here. Okay, so first you have drying. Actually, water is going to evaporate, and around 200 degrees, you start to decompose. So first is hemicellulose, then cellulose. Okay, then lignin. You have all sorts of compounds here. Here at the end, you have what we call synthesis gases, which is mainly CO and H2O. Okay, this gas is very important because you can use it as a feedstock for other compounds, for plastics, for solvents. Okay, so this is a very important feedstock. You also have some oily material that you can use. Okay, so the idea is that when you heat in the absence of oxygen, you start to decompose because these very complex molecules start to vibrate and shock between each other, and they're going to start breaking down in small parts. Since you don't have oxygen, you don't have this very energy intensive reaction that is combustion, and you have these small parts being formed. If you heat enough, you're going to end up with CO2 and H2O. Okay? So this is the thermochemical decomposition, anoxic thermochemical decomposition. And depending on the temperature ranges and pressures, you have different types of reaction. I don't know if you like coffee. I'm really fond of coffee. I really would like to have some coffee right now. But torrefaction is one type of thermochemical decomposition. Okay, you get coffee grains, you heat that between 200 and 300 degrees in the absence of oxygen at room pressure. Okay, you get coffee roasted or torrefied coffee beans, which you can grind and then make a very, very good coffee. Okay, but other types of reaction, gasification, for instance, occurs between 500 and 1300. Okay, at low pressures. Pyrolysis between 300 and 600, and liquefaction. You see, depending on, well, they are more complex than this. I'm trying to simplify, but the idea is that you have different types of pathways, depending on what you want. If you want just to make synthesis gases, or syngas, as we say, you probably would like to apply this technique, gasification. And syngas you can use for power generation, but also for chemicals. This is a very, they are very easily transformed into chemical compounds. I mean, commercial chemical compounds. Okay, so this is thermochemical decomposition. This is a typical gasifier reactor. You have your feedstock. Okay, it's being transformed into syngases here, containing mostly H2O, CO2. You can use some of this gas in order to provide energy for the decomposition. Okay, so you burn that in order to produce heat, in order to decompose this feedstock. Okay, and the products, well, the liquid fraction you can use for power generation and or production of plastics and, I don't know, other chemical compounds. And the gaseous components, likewise, production of chemical compounds and also to drive a thermal power plant, a gas thermal power plant. Okay, so the feedstock is a gas produced from biomass. Okay, so you have a gas cycle from a biomass. I don't know if you, the idea here is that I don't want to pass you the idea that it's only possible to have a gas power plant with natural gas or biogas. You can drive a gas power plant with biomass, but you have to produce the gaseous fuel from thermochemical decomposition, for instance. This is very old technology. Okay, the first gas company, not from biomass but from coal, was this company, Gas, Light and Coke Company, from the beginning of the 1800s, and this gas was used for illumination, public illumination. Okay, and I remember, and I don't know if you remember this kind of, if you watch this kind of film, you always see a gas lamp here, which light is being reflected by, you know, this is Jack the Ripper, the character. Okay, well, biomass boilers are very, I mean, biomass, not biomass oxy-fuel boilers, but biomass boilers are actually water tube boilers. That means that water runs inside the tubes and the combustion gas from outside. This is a very mature technology, especially for sugarcane bagasse here in Brazil. This is a typical biomass boiler for sugarcane bagasse. So you have a conveyor belt here introducing sugarcane bagasse. The boiler is here, okay, and this cyclone and other kinds of equipment. Well, this is the preheater, cyclone, and the system in order to clean the residues. This smoke that you see here, the white fraction, is actually water vapor. Half of this typically, let me give you some numbers. In a typical, this size of boiler processes something like 150 tons per hour, okay, and with 50% humidity. So 75 tons of bagasse and 75 tons of water. Okay, and here you have something around 100 tons per hour of water, because you have 75 from humidity and a small amount formed during combustion. Okay, so this is very, very typical. I have a movie here that I can show you the process. Oh, sorry, let me just stop. This is a typical, let me see the time, a typical sugarcane mill. Okay, the trucks are unloaded here. For those that are not aware, so this is unloaded. You have to unload one truck per each 5 minutes. That's the typical time that you have. Okay, two types of unloading systems. I'm going to show you the boiler actually. Okay. Now this is separation of straw. Here you have sand and mineral residues being separated here. Okay. I'm going to stop, well, the diffuser. You can have roll mills here or diffuser, okay, depending on your, I would say, religion. Okay. So here you extract juice, and here you have bagasse. Okay, bagasse here. Okay, so bagasse with 80% humidity. You pass that through 2 roll mills in order to dewater. So you see bagasse here. 80% humidity. Oh, this is just the chain cleaning system, the diffuser's chain cleaning system. Don't bother with that. Okay, this is bagasse. First dewatering mill, second dewatering mill. Here you have bagasse, 50% humidity, which is injected in the boiler here. Okay, so it's being injected inside. It's going to show you inside in a moment. Okay, the combustion takes place here. The preheaters and so on. Yeah. So bagasse is being fed here. Yeah. Let's see. Yeah, that's the injection of bagasse. Combustion takes place here. Okay, so you have hot gases being formed here, and these hot gases will heat water from the thermodynamic cycle here. The remaining gases, the remaining temperature of the gases may be used to preheat the injected air. Let me pause here. So the remaining hot gases may be used to preheat the air that is being sent here to burn bagasse. Okay, so and this cyclone and this other equipment is for separation of solid particles and so on, in order that the smoke here does not contain excess of this type of material. Okay, yeah, that's it. I don't know if you have some question about today's class. Yeah, right on time, 5 o'clock. Okay, no questions? Okay, so thank you very much.
Thank you, teacher.
See you next week.
Thank you. Thank you.
Thank you.
Thank you.
Bye-bye.
Bye-bye. I have a question.
Go ahead.
Just regarding the thermochemical processes you mentioned, pyrol